Today we're going to work on the mean and standard deviation of binomial variables, and we're also going to revisit what we were looking at yesterday with how to figure out what you're going to put in on your calculator when coming up with probabilities. So I'm going to call this segment, what should I put in my calculator? And again, we're just picking up where we left off yesterday. So assume that we're rolling a die 4 times. We're looking for the number 6. So the probability of success is 1/6. And we're going to roll this die 4 times. So P is going to be constant, N is going to be constant, and let's look at a bunch of different scenarios. So I'm trying to figure out what's the probability of success where X equals 3, meaning what's the probability that I could roll a 6 in exactly 3 times out of 4, right? So in this case, I want exactly 3. So think for a second, would this be a binomial PDF or a binomial CDF? And then think about what would the X value be? Well, this one is pretty nice and straightforward. We know that it's exact, so it's going to be perfect, so it's binomial PDF, and the X value is 3. That one's straightforward. Let's take a look at this next one. What's the probability of success that X is less than or equal to 3? So really what I'm looking for, another way to write that is I'm looking at what is the probability of success that X is less than or equal to 3, so that's X equals 0, plus the probability that X equals 1, plus the probability that X equals 2, plus the probability that X equals 3. So in this case, I want a range. So think, is it binomial PDF or is it CDF? And if it's a range, I want CDF. But the question is, what is the value? Now, when I'm using CDF, the value is always less than or equal to, so this X value is also 3. So the binomial, it would be CDF this time, and my X value is 3. Let's try a more challenging one. Our calculator can't do greater than. It can only do less than and equal to, or less than or equal to. So in this case, again, I have a range, so I know I'm going to use binomial CDF, but the question is, what is the X value? To think about that, I look at this and be, well, what is greater than 3 means? It means the probability of just X equals 4, and that's it. So how could I write that another way? I could write that as 1 minus the probability of all the other things, right? The probability that X equals 3, and the probability that X equals 2, and the probability that X equals 1, and I'm going to run out of room, plus the probability that X equals 0. And I could find all those probabilities, add them together, and then subtract, and then take 1 minus that. And that would give me what's the probability that it's greater than 3. So that's what I'm going to do on my calculator. Since I can only do less than, I'm going to go 1 minus CDF, and my X value is 3 because 3 would be included here. Again, because another way to look at this, the opposite of this, is saying, well, this is really 1 minus the probability of X is less than or equal to 3, because I need to include that 3. So that's another way to write that. Let's get even trickier. What's the probability that X is greater than or equal to 2? Okay, so in this case, again, I'm looking for the probability greater than or equal to 2. I'm looking for 2 plus 3 plus 4. So if I think about that, that's the same as saying 1 minus the probability of X is less than or equal to what? Well, 2 is already included here, 2, 3, and 4, because that equal sign has 2. So it's 1, right? So this one is 1. So that's what my X value is going to be. Again, it's a range, so it's CDF. So I would say, look, it's 1 minus the binomial CDF, where the X value is 1. So really what you want to do when you see this problem is you want to turn it into, what can I say? It's 1 minus the probability of X is less than or equal to what number? And that's the number you put in for your X value. And that's how we do this. Okay, nice work. Let's go on to mean and standard deviation. really what we're doing today is we're looking at calculating the mean and standard deviation of a binomial variable. Now, if you remember, a binomial variable is just a discrete random variable, so we actually know how to do this. So this is a probability table for the number of doubles in 4 attempts. So this x is following a binomial distribution with n is 4 and p is 1/6. So this is back to the doubles problem that we were looking at yesterday. So here's the probability of number of doubles that you could roll with die in 4 attempts. So looking at this, I think the next question I would ask you would be like, well, let's describe the distribution. So to describe a distribution, we start with shape. And I would look at this shape and I would say, this is skewed to the right, right? You're rolling a 0 or 1 set of double is a lot more common than rolling a 3 or 4. So the next thing I would ask you is, well, what's the center? And you would say, well, okay, I'll calculate the mean. Now we've done this before. We know the mean for x is going to be every value, like 0, times its probability, plus the next value times its probability, and so forth and so on until you get a mean of 0.667. So that's something that we know how to do. We also know how to describe the variability by talking about the standard deviation. And we know that formula as well, or we know how to calculate the variance of x. And that one's long, so let's take a look. So I have to take every single value, subtract the mean, square, times the probability. And I have to do this every single x and probability, and that just gives me the variance. So then I would have to take the square root, and then I would end up with 0.746. So that's a doozy. But what I want to show you next is the shortcut we can do with this. Okay, so I put the mean that we just calculated of x to be 0.667 in the upper right-hand corner, and then the standard deviation of 0.746 up there as well. So essentially what we're doing here is we're looking at a shortcut. So to think about the shortcut, we got to think logically for a second. We know that we want to try this in 4 attempts. We also know that the probability of rolling doubles is 1/6. So we're going to do 1/6. We're trying to get 1/6. The probability of getting for the first trial is 1/6, right? But it is for the second and the third is 4. So we're going to do this 4 times, and the probability of each is 1/6, right? So what did I do here? I just did n times p. And if I do this 4 times 1/6, I get 0.667. So instead of all of that difficult work that I had to do before, I found that the mean is just n times p. And this is one of the shortcuts that we can use when we have a binomial. And this is why we bother to check with a binomial, because this is so much faster than doing what we just did on the previous slide. So here are our shortcut formulas so that you can write them down. So we have mean and variance, and I'm going to give you standard deviation as well. So here's the thing. If I know that something has a binomial setting and it fits all the conditions for bins, then I know that mean of x is n times p. I also know that the variance, the standard deviation of x, is n times p times 1 minus p, which is just number of trials times number of successes times number of failures. And if I want the standard deviation, I just take the square root of that. So these are the formulas. Again, why bother with bins? Because this is so much easier than doing it the long way. And you might be like, are you sure that this is how this works? Well, let me very quickly show you the algebra that you don't have to know, but just in case you're dying to know, how did she come up with those amazing shorthand formulas? Let me show you. Okay, so here's where they come from. Imagine we have one trial where B is the results from that trial. And it's some chance process. If success occurs, then B is 1. If failure, B is 0. So let's just take a look at how we would calculate this. So 0 is failure and 1 is success. So if I'm looking at this, the mean is just 0 times 1 minus P, because again, 1 minus P is failure and P is success, plus 1 times P, and that just equals P. And then if I do the variance for this, and this is again just one trial, if I do the variance for this, here's all this fun algebra, and I get P times 1 minus P. But in reality, we don't have one trial. We have multiple. So if we think of X as counting up the number of successes and independent trials, then each trial has that probability of success. And X is a binomial random variable with parameters and P, then take a look at this. So if I'm trying to find my total for the mean of X, I would take the mean of the first and the second and the third and the fourth and the next one, which we just looked at in the previous example and said, well, that was just, the mean is just P. So really, if I'm adding them all together to get my total mean, then okay, it's the mean for each trial is just N times P. And then the same is true for this variance, right? If I'm just adding them all up together, then it's N times P times 1 minus P. So that's where the formula comes from. Do you have to know this? Absolutely not. But just in case, there you go. So now what we need to do is we need to talk about sampling without replacement and the 10% condition. Sampling without replacement creates a bit of a problem. To remember this, you can think about the Forrest Gump box of chocolates problem, or just thinking about taking a deck of cards and pulling the card out but never putting it back in. Whenever I don't put the card back in to a deck of cards and I'm trying to figure out the probability of picking an ace, if I don't put the card back in, my probability changes. Just like when we ate a chocolate from the box of chocolates, that changed the probability of each thing. So, okay, the probabilities change. That's a problem though, because we need them to stay the same in order for this to work. So what amazing people have figured out is they figured out that, like, look, as long as we have a really small sample, right, then it doesn't matter. The standard deviation should stay the same approximately. So we have this thing called the 10% condition. So when taking a simple random sample of size n from population of size big N, if n is less than or equal to 1/10 of the population, we're good. So I tend to look at this condition because if this is the case, then I can use a binomial setting. Then I know that my standard deviation probably is not varying that much. How do I tell this in real life? I just go, okay, well, I take the sample size and I say sample size, which again is little n, and I multiply it by 10, right? So I say sample size, times 10, and then I see what that number is. And then I just say, I'll say it's like, let's say it's 730. Then I would say the population is greater than 730. So we're okay. Right? So that's one way you can check. There's different ways that you can look at it, but that seems to be the easy one. Is just take the sample size, multiply it by 10. If the population is greater than that, you're good to go. We can use a binomial setting. Again, why does this work? Because if I'm only taking a small sample of the entire population, I'm only looking at 1 or 2 cards in the deck, it won't change my probability of success for each one if I'm only taking a small sample. So we know that if we have a normal distribution or an approximately normal distribution, we know that we can take a z-score, we can look at probabilities and we know that we have some sort of a normal curve. And that helps us greatly in stats life. So a rule of thumb for figuring out if we have a normal approximate, like if we can say a distribution is normal, is with this thing called a large counts condition. So if both of the following is true, you can approximate with a normal distribution in a binomial setting. So what I'm going to do is be like, well, if n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, then I can say, you know what, my sample size is large enough that this is going to be accurate, that I'm going to have enough samples that I should have a normal approximation. If I just take one sample or two sample, right, it's not going to accurately reflect the population, and it probably isn't normal. It's probably skewed to one side. So the larger I can get, the more it's going to represent the population, and the more that my curve will look normal. So I know I just said two contrary things. I want as big of a sample as I can have, but also a small sample size, right? So I guess really what you want to do is you want to try to aim for about 10% of the population if you can, because that gives you a large enough sample, but keeping with that 10% condition. So you have to check both of these to make sure that they work. All right, let's try a problem. Engineers define reliability as the probability that an item will perform its function under special conditions for a specific period of time. A certain model of aircraft engine is designed so that each engine has a probability of 0.999 of performing properly for an hour of flight. Company engineers test an SRS of 350 engines of this model. Let X equal the number that operate for an hour without failure. So we're going to start by explaining why X is a binomial random variable. So maybe pause it for a second and think. Okay, so why is X a binomial random variable? Well, let's start with our bins, binary. Success operates for an hour without failure. Failure does not operate. So yeah, absolutely, binary, check. I have success, I have failure. Let's look at independent. If one engine operates, it shouldn't affect the other engine. So technically each engine should be independent of each other and shouldn't depend on whether or not the other one works. So we're there. Number of trials. So we're looking at 350 engines, so we have a set number, so we're there. And then is the probability of success the same? Yes, it's 0.999. So we know that this is a binomial setting where n is 350 and p is 0.999. The next part of the problem says find the mean and standard deviation of x, interpret each value in context. Let's tackle that on another page. Okay, so we're going to find the mean and standard deviation of x and then interpret each value in context. So for the mean, I'm just going to use our new shortcut of n times p, and for the standard deviation, I'm going to use our new shortcut of the square root of n times p times 1 minus p. Again, these are in your blue book, but go ahead and give it a try. See if you can calculate the mean and standard deviation and try interpreting. It's fun. And then you can pause the video and then I will reveal the answer when you come back. Okay, so looking at the answer, I did n times p, so 350 times 0.999, and I get 349.65. So if we were to test 350 engines over and over again, we would expect that on average, 349.65 of them would operate for an hour without failure, which is kind of a funny number. It's like basically most of them. So then standard deviation again, n times p times 1 minus p, and I take the square root. So 350 times 0.999 times 0.001 equals 0.591. And then for this one, I would say in individual tests, we would expect to typically find, I should have put typically, find the number of engines that operate for an hour without failure to vary from the mean of 349.65 by an average of 0.591. And there is both the mean and standard deviation in context. So the next part of this problem says 2 engines failed the test. Are you convinced this model of engine is less reliable than it's supposed to be? And they gave us a huge gift here by saying compute x is less than or equal to 348. They don't always do that. So where did they come up with that? They're like, look, 2 engines have failed. That means 348 are good. We want to know what is the probability that we could possibly get 348 engines that are good or even less than that. So they're looking at x is less than or equal to 348. So, okay, probability that x is less than or equal to 348. I am just super excited because this is the less than or equal to, and that's what my calculator does. So I'm going to say, I'm going to do one of these so that they know what I'm talking about, show my work for one of them. So I might be like, well, 350, 348, right? Probability of success, 0.999 times 348 times 0.001 times 2 plus ... right? And then I'm going to say using tech, right? I'm going to do a binomial, again, CDF because it's a range. And I'm going to say my trials are 350. My x value is 348, and my probability is 0.999. And when I do that, I'm going to get 0.0486. But I'll show that to you on the calculator. So for this one, since it's less than or equal to 348, I know I have, I know I'm not doing PDF, I'm doing CDF. So I'm going to go into distribution, so second vars, and I'm going to arrow until I get to binomial CDF because I have a range, not a precise. I have some sort of continuous range. So CDF, so I'm going to hit enter. And in this case, I have 350 engines. I know that the probability is 0.999. And then my x value that I was given was what's the probability that x is less than or equal to 348. So I put in 348. And then I go ahead and hit paste. And I get 0.04859. The other way I could do this problem is the really hard way. So if I want to know the probability that x is less than or equal to 348, I could do this by hand. The easiest way to do this, though, is go 1 minus 349 and 350. So that's probably what I would have done. I would have said 1 minus the probability that x is less than or equal to or greater than or equal to 349. And the way that I could do that is by saying, okay, well, it's 1 minus the probability that x is equal to 349 minus the probability that x is equal to 350. You know, that kind of a thing. So I would do this, if I wanted to do this a long way, that's how you could do it by hand. Again, you get the same answer. But really the question is, use this to justify your answer. So let's explain that for a second. We get a 4.8% chance. Y'all, that's smaller than 5%. So what does that mean? That means that this should not have happened, but it happened anyway. So then I would be like, there's about a 4%, there's a 4.8% chance, is probably what I should have said. So there's a 4.8% chance that 2 or more of the engines will fail. Since that's such a small chance for 2 or more engines to fail, we are convinced that they're less reliable than they're supposed to be. Meaning that if they're true about these numbers and this probability, then there's no way that this could happen, but it happened anyway. So liar, liar, pants on fire, they are lying to us, and their claim is probably incorrect. So now you can take the rest of this time to work on your sapling. Have a great day.